Okay, welcome back. Let's see if we can get through this next section without any serious mistakes. We're looking at section 6.5. We're going to do some more really cool graphs.
Mr. Peer,
Yes?
the way you tried to wear your mask in the previous video was really stupid.
Are you saying that I was stupid?
I didn't mean it that way.
Yes, you did.
Mr. Peer, what are you doing?
I'm writing you a detention.
You can't give the imaginary student detention.
You just watch me. Okay, this one goes to the office, and this one goes to you.
Ow! Thanks, Mr. Peer. I needed that.
You're welcome.
I'm okay now.
All right, good. All right, section 6.5, let's move on. First of all, do you remember how to find your basic trig values? It's been a long time. I mean, we had Easter break, and who knows how long ago it was before that. To find the values of the trig functions, let's do tangent of negative pi over 3. First of all, where in the world is pi over 3, or negative pi over 3? Negative means we go that direction. Pi over 3 is going to be 60 degrees that way. So pi over 3 sits about like that. Where this would be 60 degrees, this would be 30 degrees. As you know, I lean toward using SOHCAHTOA. SOHCAHTOA. Tangent is opposite over adjacent. Oh, by the way, first of all, in a 30-60 triangle, if we call the hypotenuse 1 for a unit circle, then the short leg is 1/2, and the long leg is square root of 3 over 2. But we're going downward, so this is actually negative square root of 3 over 2. Remember, that's a fact that we can either use now or we can not worry about it now by using all students take chemistry. All students take chemistry says that tangent is only positive here and here. Therefore, we know it's going to be negative in the fourth quadrant. So finding the tangent of negative pi over 3 is going to be opposite over adjacent. That's going to be negative square root of 3 over 2, negative square root of 3 over 2, over the adjacent, which is 1/2. And then to divide by a fraction, multiply by the reciprocal, the 2's cancel, we get negative square root of 3. Done. All right, another one that we need to remember how to do. How about the tangent of pi over 2? Tangent of pi over 2. There's 0, there's 1 pi. Remember, the complete circle is 2 pi. 0 to 1 pi. Here's 1/2 pi. We're talking 90 degrees. So we make ourselves a little pretend triangle here. We just kind of make it really close in there. It's a little right triangle. But in reality, if we were actually at pi over 2, how wide would the adjacent side be? It would actually be 0. And the hypotenuse, which is 1, would be the same as the opposite side, which is 1. So now what's the tangent? TOA. Tangent is opposite over adjacent. That would be 1 over, can't have that. Well, the tangent of pi over 2 is undefined. That's going to become important to us. So the tangent of pi over 2, because we can't divide by 0, is undefined. It doesn't exist. No such thing. Now, with those things in mind, we're now going to attempt to graph the tangent of x. We're going to graph y equals tangent of x. Now we're going to lean heavily on the book here. The book gives us a bunch of values, page 401. They did the work for us. We don't have to figure out the tangent of all these different points. We simply read it from the chart here on page 401. How convenient. You could figure these out for yourself, but let's not take time for that. So we know that the tangent of 0 turns out to be 0. Look at your unit circle, you'll see that to be the case. Then the tangent of pi over 6 ends up being the square root of 3 over 3, and the book tells us the square root of 3 over 3 is about 0.58. So if this is 1, tangent of pi over 6 would be about 0.58, so we're talking about someplace right about there. The tangent of pi over 4, we could figure out, is 1. The tangent of pi over 4 is 1. The tangent of pi over 3, as we just saw, is about 1.73. The square root of 3, about 1.73. So it's about 1.73. It's up here someplace. And guess what? As we get closer and closer and closer to pi over 2, which is undefined, this thing gets steeper and steeper and steeper. In other words, we're going to have ourselves something we haven't seen in a long time. We're going to have a vertical asymptote right here. If we go in the negative direction, we find the same story but in reverse. Negative pi over 6 would give us a value of, what was this, negative 0.58, I believe it was, right about here. Negative pi over 4 would give us a value of negative 1 right there. Negative pi over 3 would give us negative 1.73, which is someplace down about here. And if we connect these points with a smooth curve, remembering that this becomes an asymptote, and so does this, we have something that looks kind of, whoops, stay up there, something that kind of looks like this. That is one complete cycle, because once we get past pi over 2, the whole thing repeats itself. It jumps from basically positive infinity to negative infinity and repeats itself, passing through pi and heading toward 3 pi over 2. Then it repeats itself, it flips down here again and heads from infinity through pi over 2, heading toward 5 pi over 2. And then it flips itself again, starts down here, heads toward 3 pi and up toward 7 pi over 2. And we have all these neat asymptotes here and here and here. Notice it passes through the x-axis at 0, at 1 pi, at 2 pi, at 3 pi, guess where else? At 4 pi, 5 pi, 6 pi. We mentioned back in some previous section that tangent repeats itself not every 2 pi like sine and cosine, but tangent repeats itself every 1 pi. We can see that here. Every 1 pi, it repeats itself. It's easier to see it from asymptote to asymptote. How far is it from here to here? That's a space of 1 pi. It repeats itself every 1 pi. So the period is 1 pi. That's why the period formula is that period equals not 2 pi over omega, but 1 pi over omega. Now, what else do we need to mention about that? Not much. From there, we certainly could do some transformations. The book suggests, some of these, they're going to introduce something I don't remember seeing them do with sine and cosine. Did they ever do it? I'm flipping back for just a moment here. And I don't believe they ever addressed, no they didn't. Okay, they're going to now. We're going to clear this. If I clear this, I'm going to get rid of all my pi. I got rid of everything. Didn't mean to do that. I'll tell you what, let's just reload this file. Stand by a moment. Sorry to waste your time here. Let's close. Let's not save. And let's reopen. Open recent trig coordinate plane. And there it is. Okay. So, Let's consider what happens if we have y, didn't mean that either. If we have y equals a times the tangent of omega x, and this time what we did not see the book present to us with sine and cosine, we're going to throw in a plus b. But you already know what that does. Plus b is simply going to shift it up or down. A positive b would move the whole thing up, a negative b would move the whole thing down. No big deal. You already know what a does. A changes the amplitude. But tangent doesn't have a maximum or a minimum. So the amplitude simply tells us that, for instance, instead of having a value of 1 up here, we would have a value of, if a were 2 times tangent, we would have that point instead of this point. It would make the whole thing get stretched. Then what about omega? Well, remember your period is pi over omega for tangent. So putting all that together, let's see if we can just grab an example here. Let's take the example of trying to graph 2 times the tangent of, oh, there they're throwing the x minus 1 thing. So let's do 2 tangent of x minus 1. It's important that that 1 be outside the parentheses. We're not trying to do x minus 1, but we're taking the whole function and subtracting 1, which is going to shift the entire thing down 1 unit. So, tangent of x. We know what tangent of x looks like. Tangent of x kind of looks like, it goes through, by the way, it goes through, I'll get this straight, pi over 4, 1, and negative pi over 4, negative 1. Hopefully I've got that right. It goes through pi over 4, 1. Yes, okay. I'm afraid I'm going to mess this up if I'm not careful. So that is pretty much what tangent looks like. But 2 times tangent says, instead of this point, we're going to have this one twice as high. Instead of this point, we're going to have this one twice as low. It makes the whole thing get a whole lot skinnier. It still approaches the same asymptotes, but it's skinnier. And we would have the same thing repeating. Now, what does the omega value is 1, so it still has a period of 1 pi. So it goes from a half pi to a negative half pi. Watch out for that. When you're doing the first one, remember, tangent passes through 0, 0. If its period is 1 pi, then it has to go a half a pi this way and half a pi that way for a total of 1 pi. And then another 1 pi. And then another 1 pi. And then another 1 pi. The minus 1 part here says we would take this now and take the yellow guy and take this point. Oops, wrong tool. There we go. Get rid of that. Get rid of that. Take that curve and just slide it down 1 unit, which makes for kind of an ugly graph. It's hard to tell. On tests and such, I don't care for the B part because with tangent, it's really kind of hard to see the difference. It gets a little bit messy. So we'll see how that goes. All right. Let's take a look at this one. If I can clean this up by erasure. Okay, let's look at, good. Let's look at y equals 3 times the tangent of 2x. All right, again, it's got to start, or it doesn't start, it passes through this point. This time, omega is 2. So the period is going to be pi divided by omega. The period this time is only a half pi. Well, if the period is a half pi, that means we must go a fourth of a pi this way and a fourth of a pi that way. Don't think, oh, omega is pi over 2, so, or I'm sorry, the period is pi over 2, so I'm going to go over to pi over, no. The period being pi over 2 means from here we're going to go a fourth of a pi that way and a fourth of a pi that way for a total of 1/2 pi. And instead of going through 1 here, it's going to go 3 times higher, and I can't put it on the graph. So it's going to be super tall and skinny, and it's going to kind of look like that. Oh, that's pitiful. This doesn't look like an asymptote at all here. But it approaches this asymptote, and over here, that was pitiful also. It approaches this asymptote, and then of course it repeats itself. Same thing here, same thing here, same thing here. With tangent, really showing the amplitude is tough. Then having weird amplitudes mixed with a b value makes it even nastier to try to graph these. I confess, it's nasty. Now, what about cotangent? Do you remember the definition of cotangent? You had better. Cotangent is simply the reciprocal of, yes, I heard that. Cotangent is the reciprocal of tangent. So if we consider just y equals tangent of x again. Y equals tangent of x, it goes through 0, 0. It goes through 1/4 pi, 1, negative 1/4 pi, negative 1. And it looks kind of like this. All right, that's tangent. Now what about cotangent, the reciprocal of tangent? Cotangent of x. We need the reciprocals of all these things. Well, first of all, let's do it in white. What's the reciprocal of 1? Negative 1. No. The reciprocal of 1. Take a 1 and flip it upside down. The reciprocal of 1 is 1. 1 is its own reciprocal. So it still passes through this point. But now think about this a second. What caused this asymptote to be a problem? What caused it, remember, is that we had 1 divided by 0. So what's the reciprocal of 1 divided by 0? The reciprocal of 1 divided by 0, if there were such a thing, would be 0 divided by 1, which equals 0. So in a weird sort of sense, one could sort of say, and if any other math teacher heard me say this, they would probably revoke my license. The reciprocal of infinity is 0. So instead of having an asymptote here, it actually passes through 0 here. Interesting. But then what's the reciprocal of this point? This was the tangent point. It passed through 0, 0. What's the reciprocal of 0? Well, it doesn't exist. But the reciprocal of 0 would be 1/0, which becomes another asymptote. So we actually have an asymptote where we used to have a 0. So what's this thing end up looking like then? It looks kind of weird. Did I put this in the... Yes, I did. That's in the right place. So it looks like this. The points that used to be zeros for tangent become asymptotes for cotangent. And the points that used to be asymptotes for tangent become zeros for cotangent. So every place where tangent gave us a 0, we put an asymptote instead. And every place where tangent gave us an asymptote, we put a 0 instead. The asymptotes and the zeros swap places. And instead of passing through 0, 0, it passes through pi over 2. So if you remember this then, if you know what tangent looks like, okay, I think I've got that, good. If you know what tangent looks like, then you might just kind of lightly sketch in tangent first. Then remember, for tangent, what was a 0 becomes an asymptote. And for tangent, what was an asymptote becomes a 0. Remember also that it tilts, instead of to the right, it tilts to the left. And it still passes through the same point here of 1/4 pi 1. What else? And it still has a period of 1 pi. So it repeats between 0 and 1 pi. It repeats again between 1 pi and 2 pi. It repeats again between 2 pi and 3 pi. And it looks something like that. That would be cotangent. You might want to play with that on Desmos. I don't remember, does Desmos include cotangent, secant, and cosecant? I think it does. If it doesn't, you can fake it by simply putting into Desmos for cotangent, put in 1 divided by tangent, and it'll give you cotangent. And you can see what the graph looks like. But I think it does have cotangent. I think it has the reciprocal functions. I'm just not going to look at it right now. All right, now, that's cotangent. Let's take a look at secant. Secant's fun. Got a lot of erasing to do here first. Rather than reloading the file, I will try to erase everything I've done here up to about where? Up to about there. All right. Now, in fact, we can get rid of this too. Now we're going to look at secant and cosecant. I like secant and cosecant. They're pretty cool. First of all, we know what y equals sine of x looks like. No problem, right? We're well familiar with that now. Sine starts at 0, 0. It has a period of 2 pi. It has a maximum of 1 halfway, or it goes through pi also. Has a maximum of 1 at pi over 2, a minimum of -1 at 3 pi over 2. We know what sine looks like. And we can continue on. And there we go. All right, now, I think I really botched this, and I can't leave it like that. I can't leave it like that. That's a little better. Okay, now, the reciprocal sign is what? Remember, sine, cosine. For those, by the way, who are new to these videos and have not seen my previous actual real-life in-class lectures, I don't recall if we've done this in the videos or not. Mr. Sullivan, by the way, for those who have always wondered what book we're using, this is Sullivan's Precalculus. This is the 8th edition, still available online. It's fairly old now, but it's a good one and still available, used. You might be able to get it new, but it's whopping expensive if you buy it new. Anyway, if you write down the functions of what I call the natural order, and not Hewitt, Sullivan never does this. Sine, cosine, tangent, cotangent, secant, cosecant. Where are the reciprocals? You do these brackets. Those guys are reciprocals, those guys are reciprocals, and those guys are reciprocals. Makes it really easy. So, back here, the reciprocal sign, therefore, will be y equals cosecant of x. So how do you graph cosecant of x? Let's start doing some reciprocals. How about the reciprocal of 1? That's easy. The reciprocal of 1 is 1. So it still goes through that point. Hey, what's the reciprocal of -1? -1. It goes through that point. What's the reciprocal of +1? 1. It goes through that point. And through that point. And you might be saying, wait a minute, it's going to look just like sine. No, it's not. 0. What's the reciprocal of 0? Oh, it's an asymptote. Right, it's going to be an asymptote. So in some weird way, we're going to end up with an asymptote where we used to have a 0. We're going to have an asymptote where we used to have a 0. We're going to have an asymptote where we used to have a 0. We're going to have an asymptote where we used to have a 0. I did mess this up. Oh, I messed that up radically. That was not where that belonged at all. It was supposed to go through here. Yeah, that's why it looked so weird to me earlier. Anyway, where we used to have a 0, we'll have an asymptote. All the zeros become asymptotes. So what do we do with that? Well, we could plug in some numbers and see what happens, but we're not going to take time for that. Just trust me that if we were to come up with numbers, perhaps pull out a calculator, get some values for different positions on the x-axis, we would see that it looks like this. Let me do it in red. I hope the red stands out well on the video. It's going to do something like this, and this, and this, and this, and of course this. Pretty cool, huh? The reciprocal of this value would be up here. If this is 1/2, it would pass through 2. If this is 1/2, it would pass through 2. We can see my graph's not very accurate. If this is at 1/2, yeah, there we go. Yeah, if this is 1/2, then directly above it would be, oops, 2. Not too bad. Here, where it's 1/2, the reciprocal would be 2. Ooh, I kind of missed on that one. There. So you end up with this interesting shark tooth kind of pattern thing going on here, I guess you could call it. Those are awfully dull shark teeth. Anyway, so to graph this is very simple. You get an idea of what it looks like, and you recognize that it passes through each minimum and maximum point, and then it just goes up and down, and up and down, with asymptotes halfway between these maximum and minimum points. So halfway between these two, there's an asymptote. When you draw your graphs, don't you let those things cross the asymptotes. Halfway between this minimum and maximum, you'll have another asymptote. Halfway between this maximum and this minimum, you'll have another asymptote. Well, what about, I got secant. Secant being the reciprocal of cosine. Well, that becomes very easy now. Let's, tell you what. Let's break down, I can't resist. Let's go ahead and take a look at Desmos and look at secant. Secant. I need to go here, and I need to go to there. Haven't seen Desmos in a while. Let's go full screen. Okay, and let's get my keyboard up here. And I'm not going to worry about exact locations here. Oh, I could. If we hit the little wrench up there, let's have it step pi. Where's pi? There's pi. Is it that easy on the x-axis? If I tell it yes, that's what I want. Yep, there we go, good. So now we have ourselves 0, 2 pi. I don't know if you can see that, it's kind of small. 2 pi, 4 pi. Okay. So, let's graph, first of all, cosine. So I want y equals function cosine, there it is, cosine of x, and there's cosine, no surprises, right? It passes through 0, 1, has a period of 2 pi, no surprise. Now, you can probably guess what secant is going to look like, because secant is the reciprocal of cosine. Let me see if I can graph it on here first, just for fun. Let's do it. Let's do it in green. Kind of dark, it'll show up better. So, secant should pass through this same point, and this point, and this point, and this point, and this point, and that point. But then it simply kind of goes in what you might call the opposite direction, with asymptotes halfway between. So we got an asymptote here. It's going to go kind of like this and this. Here it's going to do that and that, being careful that I keep my asymptotes in the right place. What was a 0 becomes an asymptote. And this goes here and here. This goes here and here. And this one here and here. this one here, and here. These are very easy things to graph once you know what cosine looks like. Now let's ask Desmos if it agrees with us. So we want y equals, and does it give us, yes it does have all of them. It's got cosecant, secant, and cotangent down here. So I want secant, and let's see how it handles it. And, oh, I need my x. There. And look at that, pretty good. Yeah, my sketches, okay, pretty good. I call it good, but yeah, it didn't match up perfectly, but certainly kind of, sort of came close. And that's, if I erase my stuff, you can see Desmos' stuff better. And there's your secant function. All right, nice, huh? Okay, so you can play with Desmos to help you see how these things work. And you know something? I'm not going to bother with any of the transformations. Well, maybe there's one that would be helpful. Let's consider what happens if I have, for instance, 2 times cosecant, well, let's stick with this one, 2 times secant of x. Let's do 2 secant of x. Well, 2 secant of x would be just like secant of x, except instead of starting at 1, it starts at 2. So secant should be kind of like this, and kind of like this, and kind of like this, and this. You get the idea. Instead of starting at -1, it starts at -2. Instead of starting at +1, it starts at +2. So it separates these little teeth by more. It doubles the separation. So now if I ask it for, let's change it from secant to, oops, wrong tool. If I change it from secant to 2 times secant, there it is. The new blue graph matches up with my green ones rather nicely. You can see it right there, and you can see it right there. All right, so that's everything you ever could have wanted to know about graphing tangent, cotangent, secant, and cosecant. You might need to watch this video about 10 times to really get it down solidly, or you can refer back to the book and look at their examples, and you can play with Desmos. By the way, for those who are new to this, Desmos is a free website. You just go to desmos.com. It's DESMOS.com. And it's a marvelous tool. It's free. There's no advertisements, no nothing. Just go there and use it. It's better than a graphing calculator, really. It's a lot easier to use and more accurate and more versatile than even a TI-84. Really, it's very nice. I just wish it were in a small enough package you could take it with you in a calculator. But yeah, really nice help for you. Okay, and we're done. Oh, assignment. Oh, I didn't figure out what the assignment was going to be yet. Let me see. Oh, sorry to have to take your time again. I've got to take some time now rather than making this a second video just to give you the assignment. What did I give last year on this? This is section 6.5. Last year for section 6.5, I gave the following. First, I've got to get rid of Desmos. Come on, we can do this. Okay, go away, thank you, at last. Okay, so your assignment is on page 407. That makes sense? Yes, it does. Numbers. Let's do 17. I don't remember why, but I'm taking my word for it from last year. And 20 through 40 by 4. And is that all I gave? That just doesn't seem like enough. That's it. 17. What's special about 17? By the way, I also see a note here that it just caught me by surprise. This Corona thing has really messed up my mind. But it looks like we actually just finished the chapter also. Anyway, number 17, okay. Oh, I just didn't want to torture you too much with tangent. That's why there's only one like that. And then we jump down to number 20. Yeah, I do not remember why I did it that way. But that's it. There's your assignment. This will be due on Friday. At noon. Okay, that's it. See you later. And now we'll see how long did I go. I have no idea. Hopefully not too long.